I'm from Colorado, and I work in the Rocky Mountain Research Station. And today I'm going to present kind of a grab bag of our research for the last 10 years. Hopefully it will be more or less coherent. I have a lot of different projects. I showed all of my collaborators. This is just sort of the PIs, and then there are a lot of different folks that work with us. I know some of you have interacted with some of these people. So I'm going to try to pluck highlights from various studies, and many of these things I've kind of thrown into this talk after hearing things yesterday. So if it's a little bit patchy, please forgive me. So the Fraser Experimental Forest, which is sort of my headquarters or base of operation, is about 100 miles west of Denver. And this part of the Rockies is sort of a key area for watershed research, and many of you are forest hydrologists are probably familiar with the paired watershed experiments that have been done at Fraser. This is the Full Creek East St. Louis experiment here in an old-timey Forest Service picture showing the control watershed and a treated watershed next to it. This area is very important in Colorado because it's the headwaters of 5 major rivers. The experimental forest itself sits at the headwaters of the Colorado River, but about 100 yards downstream of these gauges, the water goes into a pipe and goes over to Denver. It's so valuable that they don't even let this water go down into Colorado. And this is a common situation in Colorado where we have major diversion projects going from snow-fed ecosystems up high over to agricultural producers and suburban lawns on the Front Range. So this area was set up back in the 30s to start studying these effects, what happens when you manage forests to try to improve the amount of stream flow, and then subsequently, and is there a concern with water quality? Yesterday's talk on the hydrology and some of the plot level work here was a great introduction to this type stuff. And there have been sort of 2 major players that have been identified, and research at Fraser has sort of focused on these over and over again since the 30s, looking at how the effects of the forest canopy and water use influences the amount of stream flow. Of course, what everybody wants is more of this. And the question is, do you need more or less of this to get it? And there are 2 processes, and they came up yesterday. If you affect the amount of snow that's intercepted or on the canopies, you can affect the amount of snowpack and ultimately the amount of stream flow coming out. Similarly, the other player is one that came up yesterday. If you snip these trees, you take water away from these straws, as we like to think about them in a watershed perspective, and you save more water, and you can create more stream flow. Studies at Fraser have showed significant increases in stream flow. They're long-lasting, and they're also advance the timing of the stream flow. So, for example, this is a graph looking at the effects of harvesting in the Full Creek watershed back in the 50s, comparing it to East St. Louis. And the points I wanted to just point out, this is just sort of a relative comparison between the 2 basins. And from the time of harvest, you see almost an immediate increase in flow. So you've turned a forest into a field of stumps. Interception goes to 0 immediately because those big umbrellas up in the crowns are no longer there, and all of that snow that was caught on the canopies is now making it down as snowpack, where it's stable and it turns into stream flow. Similarly, you've snipped the ET component, and so all of that water that was going up in summer ET is now available for runoff. So you see a significant increase, and this is what has guided and encouraged people to sort of harvest for water in the West. It's a long-term effect, so over 30 years there's a 40% average increase in stream flow. And the Full Creek experiment, which was preempted by the Mountain Pine Beetle, we never actually got back to a point where we had gone back to our pre-beetle stream flow. We were projecting that it would have been around 60 years. the bark beetle came in and it changed our control basins and our treated basins, so we're never going to really know what this number was. But in our ecosystems, and similar here, I suspect these are very long effects. You remove a significant amount of the basal area and you can have a long-term influence on water. If you were to do this experiment at Coweta in western North Carolina, this story would be over in about 10 years because of the rate of trees growing back. So the recovery is a function of regaining sap flow volume and leaf area, and in our area, our forests where we have 10 months of winter, we don't really regain leaf area very quickly. So that's a little bit of the context of the science that was done at Fraser. This is the experimental forest, about 100 square kilometers, and several of the things I wanted to point out is that it kind of represents a gradient of land use typical of what we see in the Colorado Front Range. It's got two wilderness areas on either side of it, Byers Peak, Vasquez. The Henderson Mine, Steve Grossnickel and I were just talking about that, is right over here, back where he did his research. We've got managed forests where the U.S. Forest Service harvests timber for various reasons, and then we have this kind of smear into the wildland-urban interface, which is a big part of our Front Range ecosystem, where we have high housing densities, concerns with wildfire, all of the issues to do with weeds and so on. So for my talk today, I'd like to kind of focus on two different parts, and I'm hoping that these will inform the discussions about restoration and rehabilitation. The first one is kind of the results of our watershed scale study. So mostly what we've done at Fraser and seen in the Fraser Experimental Forest in unmanipulated systems. Then I'm going to talk about some of the management work that we've done, and we sort of look at these two pieces together when we're thinking about trajectory of forests and management alternatives. This is kind of a series of the train coming through Fraser. These are some of the initial spottings from aerial detection surveys. This is Grand County, and the Fraser Experimental Forest was here. We saw the first trees in 2002 that were hit by bark beetles. By 2005, things had gone sort of wall to wall, and by 2007, most of our experimental watersheds looked like this. Probably seen the same thing. So the folks that are represented on that first page, there isn't a single entomologist on that list, and none of us really know much about bark beetles. The biology of bark beetles eludes us, and frankly, we don't really care about it, I hate to say. We're looking at the effects of the bark beetle, and we're ecosystem ecologists or watershed hydrologists, and we're interested in how this disturbance will influence the things that people want out of our ecosystems and watersheds. And at Fraser, it's primarily water and clean water. We've learned a lot about one or two things over 70 years, and the question is any of that relevant to this new thing? So we know, and I showed you some data, that if you harvest forests, we see an increase in flow. It's a slow period of recovery, and we figure that bark beetles are going to do something like that. These are sort of the questions we had when the bugs started hitting us hard. But we really had no idea, is it going to be just like a clear cut? Will it be as fast? We assumed that it would probably be lagged and dampened, but we weren't really sure how those effects would look. And it's taken us a while to sort of tease some of this stuff apart. We know some things, that whatever happens, how that influences snow, how that influences water uptake, will probably influence our watershed yields. What's going on with nutrient uptake, it's kind of an unknown question. But the timing and sort of the interaction with the residual forest is probably key. We know what happens to the trees is key, so we know that in a bark beetle outbreak, we're not going to lose 100% of the forest. There's been very little sort of historic bark beetle work done in Colorado. One story which was followed up a windthrow and then spruce beetle outbreak in the 50s. This is near Steamboat Springs, or the Flat Tops, for those of you who know Colorado, on the White River National Forest. Looked at how stream flow changed following the loss of about 30% of the basal area in watersheds in this area. And a couple of take-homes from this was that the effects were kind of lagged. So over the first few years following the bark beetle, this is comparing infested and uninfested areas, by the way, and two drainages that had some mortality in them. You started to see kind of a gradual increase. It fluctuated from year to year or over several years, but the peak didn't happen for 15 to 20 years following the beetle outbreak. That's kind of a key point. And it stayed significantly higher for over 20 years. Now, we're at year 10 with a bark beetle outbreak in Colorado, and we're kind of comparing things, do we see something to this level or not? But significant effects takes a long time, and this sort of seasonality is what is consistent with what we've seen at Fraser with our snowpack. Depends, if you have a low snow year, you don't save much snow, you don't have much of an interception savings. In a high snow year, you're going to see a bigger increase. So it's very seasonal. There's a lot of interannual variability because of the snowpack variability. As a biogeochemist, I am always looking for the, oh my God, data to put in proposals and so on to try to make my research relevant. And there's one great example of the bark beetles can do really bad things from a biogeochemical perspective that comes out of the work in Western Germany, in Bavaria, where spruce beetle outbreaks have increased leachate nitrate up into the level where it's pinging against human health standards. Now, what we see here is this is water leaching out of the bottom of an ecosystem, so it's not actually stream flow. So that's kind of an important consideration. But it's going to the point where they're breaking some of their regulatory limits, and you see that there's a short lag, that it kind of goes up for several years, and it stays high for about 7 years before coming back down. They attributed in this study, they attributed this sort of period of recovery to, this is about how long it took for them to get grasses growing back on these sites. So the regeneration of the vegetation was key in the recovery phase. Now, the other piece of this that's very important and different from here and different from Colorado is that this area is an area with high chronic nitrogen deposition. So they have a system that's already stressed by a lot of nitrogen inputs. And basically you're seeing sort of the inability of the system to retain these additional nitrogen inputs from the vegetation. So that's kind of a little bit of background. Now I'm going to talk about some of the findings and some of the work that we've done in Colorado. And this is a study that was spearheaded by my colleague Rob Hubbard. And one of the questions that we had as we were starting to see the bugs come into Fraser was, what is actually killing the trees? I learned in forestry school that it was the fungi, and that was what I thought everybody else in the world knew, but there seems to be some argument, perhaps with entomologists, about, well, maybe it's girdling, maybe it's the blue stain, who knows. And so we did an experiment where we girdled trees, we allowed some trees to get hit, and we protected some trees so that they weren't hit in a stand, and we compared these three treatments. Basically, the data I'm showing you here are just from the hit trees, the trees that were affected by pine beetle, and the points I wanted to bring out were that this is looking at the sap flow, looking at the water that's being taken up, or evapotranspiration, if you will, and looking at that how quickly that drops off once those bugs get in the tree. Now, these trees weren't girdled; they were infected, and there was fungi moving down through the stems. Within several weeks, we lost 50% of the water uptake in those trees, and after a year, so the next spring, when these trees hadn't really even started fading yet, they were using no water at all. So the kind of quick take-home of this was, within a couple weeks, these trees are dead in terms of water use. They're no longer taking water up, but there's no visible sign that this is happening. The girdled trees, by the way, were happy for over a year. They continued to use water. They flushed new needles the second year. It wasn't until the end of the second year that the girdled trees, and we girdled a meter's worth of phloem off the tree. So phloem girdling is not the problem. And then as one other piece of information here, the foliar moisture and the flammability of those needles increased immediately. So the foliar moisture went down and flammability went up. So in terms of the fire risk, these needles posed a big hazard within weeks. So water use goes down immediately. What happens below ground? We heard a little bit about some soil effects, and we did a study looking at trees throughout Grand County, sort of the central part of the beetle outbreak, and looked at green trees that have been hit for a couple years, and gray-faced trees that have been dead for several years, and found soil moisture was higher underneath those trees. So that couples with what we saw with the water use picture, and so was soil nitrate. Soil ammonium was also higher, and various other indices of soil nitrogen availability were higher. And the interesting part is that this happened right away. So it was going on in the red-phase trees before the stands had really opened up yet. So the abiotic conditions, light, temperature probably hadn't changed very much. This is consistent with the effect having to do with the lack of uptake by the trees. So you see this, there's a lower demand and a higher nitrogen pool underneath these trees. Okay, so we have higher water higher water, more nitrate, and we would maybe expect we'll see something in the streams, right? Well, first, before I get into the watershed scale stuff, I wanted to kind of step back to our paired watershed studies, where we wanted to compare what's going on with different types of basins. And we've thought about our basins as how does removing overstory affect stream flow? And in this case, we wanted to sort of think about them as how do these treatments influence the stands that the bark beetles came into. So we have old growth forest in our reference basins, and we have what we call a mixed age stand in our treated basins now. So there's strips of old growth forest, and then there's young stands. In this case, the stands are about 50 years old. So smaller diameter trees overall in the mixed age stands, and a greater proportion of large pine in our old growth stands. Okay, so you might be getting a picture of susceptibility and how that might differ across these. And then there's also differences in the understory. So in these mixed basins, we've got higher density of smaller trees, more subalpine fir. So that might have an effect on some of the processes as well in terms of retention within the basins. Okay, so now the watershed effects, and we're looking for what happens when you increase soil nitrogen underneath trees and soil moisture under trees, and we're looking for a big nitrogen pulse during our bark beetle effect. What we have here are the two different old growth watersheds, East St. Louis, which I've been talking about, and Lexington, which is part of another paired watershed, Full Creek, which is the basin I've been showing you, and the pair for the second study, Dead Horse. And you have to look pretty closely to see much of an effect here. So East St. Louis shows a little bit, you might be able to see it, but if you think about it in the context of everything else this graph is showing, the amount of interannual variability, the difference between the watersheds, that bark beetle effect is kind of not very interesting. There are some other things that might be worth noting. The fact that in the Full Creek watershed, this was harvested 50 years ago. These nitrate numbers are extremely low. There's some pulses in certain years. Perhaps those have to do with low snowpack years and soil freezing. There are increases in nitrate following that, but they're typically almost at detection level, meaning we hardly ever find them. The Dead Horse watershed was cut back in the late 70s, and so potentially what we're looking at right here is this sort of the last bit of that harvest effect. But we don't see any kind of a harvest effect in our Full Creek watershed. It was too far in the past. Okay, so in general, we're not really seeing much that has to do with bark beetle. If we multiply sort of break things down by season and flow weight our concentrations, we do have some significant differences in our old growth stands versus our mixed stands. So we're seeing no effect of the bark beetle in our mixed age stands. Okay, in our old growth stands, both in East St. Louis and Lexington, we see 1.7 to 1.6 times more nitrate during the rising limb in the spring as the hydrograph's going up, and then also in our base flow. During the summer months, when there's a lot of nutrient uptake in the streams, we're not seeing anything. Nitrate, by the way, in these systems is about 80% of our dissolved inorganic nitrogen, and our dissolved inorganic nitrogen is the bulk of all the N coming out of these streams. Okay, so there's significant differences, so we can feel like we'll be able to publish something on this. If we bulk these in different ways and say, what does this mean to downstream users? We think about export, multiplying this by the amount over time, and start to think about it. So this is what the water users are going to get, and nitrate is a water quality concern. There's human health issues. There's eutrophication issues. So, oh my God, there's more coming out of these old growth basins during these periods of the year. So we get a little bit more out of Fool Creek, a lot more out of our old growth basins, and most of that is focused during this high flow period. So we're multiplying it by big flow numbers when we get 40 to 50% of all the flow in our peak snowmelt. Great. So we've got these significant numbers. I don't know. Many of you probably don't think about nitrogen a whole lot. So if you think about that, taking those numbers downstream, and maybe compare them with something else, they're only about 2 to 5% of the nitrogen inputs coming into these systems. So the change in nitrogen going out of these systems following the bark beetle is a small fraction of what's coming in. So we have a significant increase in a really small number. We still have very clean water coming out of these basins, so Denver water users and folks on the Front Range aren't going to be concerned about these numbers. Now, it's relevant for those of us who think about the ecosystem, because yes, they are responding. That nitrogen did go somewhere and we were successful in finding it, but it's not something that should have water users concerned. Great, so why? We're going to be looking at some things, where there's some changes in flows. This is looking at stream flow, and I've plotted SNOWPACK. We've got long-term snowpack measurements throughout our basins. Again, we've got our old growth basins and our mixed basins here, looking at our April 1st snowpack measurements, pre and post bark beetle. There was a drought before the bark beetle outbreak. We talked about that a little bit yesterday, and some other dry years since, but we're not seeing any kind of huge response one way or another that would kind of change our export numbers. There hasn't been a huge climate signal in this stuff at Fraser. A few years ago, we got together, we took this data and met with people at CU, USGS, Colorado State, and various other universities, and had a meeting very much like this, where we were comparing notes and comparing talks, and everybody was sort of coming up with the same, there's really not that much going on with water chemistry type of situation. We looked at a lot of the other sorts of disturbances following a harvest. This is the famous Hubbard Brook experiment, where they clear cut an entire basin and then poured herbicide all over the residual vegetation, kept it completely denuded for several years. You see 500–600% increases in nitrate coming out of streams. That's the textbook when you disturb a watershed type of picture here. Other clear cuts in the western U.S., partial clear cuts in various locations, all show increases of several hundred%. And our bark beetle outbreaks in Colorado are just sort of barely even showing up here. So certainly less than typical disturbances. If we look at stream nitrate across, compared to various other factors, there's a lot more going on in a watershed that affects nitrate than these years with bark beetles. So these were the percent mortality during several years in a number of drainages around Rocky Mountain National Park. And the effect of elevation, forest cover, precipitation, these all had much larger effects than, say, the bark beetle outbreak. So what's going on with bark beetle doesn't seem to be nearly as important as other pieces to the picture. Colleagues at CU were interested in sort of, looking at this a little bit more closely. This is the expected graph, kind of based on what I showed from the bar before. This is the Hubbard Brook clear-cut watershed. And given the amount of deposition in Colorado, we might expect that we'd see an increase up to several hundred parts per million of nitrate, and that would happen very quickly. What we actually seen is something more like this. So they sort of step through various pieces of the things that control this. You don't clear cut a basin, and bark beetles don't clear cut an area in 1 year. So if we smear the effects of bark beetles over time in a situation like this, where we say, okay, the watershed's being hit a little at a time over a decade, we might be able to lower the amount of nitrate that comes out. There'd be some lagging because of that. So it would take longer and it would be lower. If we decrease the amount of trees that are killed over that period, over that 8-year period, we can decrease it a bit more. And if we actually the final graph, they actually had to decrease the amount that were killed, so about 50% of the total basal area, and then also increase the growth of what was left. So they had to kind of evoke the idea that the remaining trees were growing faster. We heard a little bit of an indication that maybe that happens in Canadian forests yesterday, and so I wanted to see whether or not we could find any compensatory responses in our forests in Colorado. There was a study from a historic bark beetle outbreak in the 70s. This was up around Yellowstone National Park. Work conducted by Bill Rami, who's a retired forest ecologist from Colorado. And he did stand level measurements looking at bole growth following a bark beetle outbreak, and this was from one stand. He looked at a number of them, but showed that very shortly after the initial dieback, you see an increase in growth, which this is kind of forestry 101 and should be surprising to foresters. The fact that it was sustained at higher rates for several decades is noteworthy, though. So are we seeing that following the bark beetle outbreak in Colorado? Again, this is kind of the forestry 101 graph. Here's a tree core coming up to the harvest in Fool Creek. So this was a core in 1950 to 1960. This was the 100 years prior, and you can see how much faster those trees were growing following harvests. These were radial cores, tree ring cores from trees coming into the bark beetle outbreak. So looking at lodgepole and Engelmann spruce in our watersheds at Fraser, we found that 30% or more of the trees started growing faster following the beetle outbreak. So these are residual live trees in areas that were hit. Many of these trees, about 16%, were growing faster after the bark beetle than they were for the previous 100 years. So pretty amazing that you'd get a release response like that in very old trees in this elevation. We were able to find some correlation between the amount of basal area lost in a plot and the increases. So more neighbors that died, the faster the trees responded. So radial growth increases. Looking at the understory, looking at what's going on with advanced regen or the sapling stages and height growth, we compared our three main species and see a significant increase in growth in the years after the bark beetle came into these stands. In many cases, they're doubling. And again, we see an increase in growth in relation to the amount of basal area loss. So overstory responds, understory responds. How about biogeochemistry? This is foliar nitrogen in a tree that's dying, and it goes down. No big surprise there. The trees in the neighborhood, though, have a really nice increase in nitrogen. You see a big pulse, and so similar to what we heard about transpiration, the young trees are, in Colorado we say, sort of stepping up to the bar now, they're getting a chance to take advantage of all these available resources. And so you see an increase in foliar nitrogen following the beetle outbreak. This has been seen in other studies in Colorado as well. Okay, so we see some evidence of compensatory growth, changes in foliar nitrogen, height growth, radial growth. And so kind of going back to our stands a little bit and thinking about putting some of these pieces together here. This is what one of our old growth basin looks like. It's sort of dead wall to wall, and our famous red hand of death picture kind of demonstrates what our mixed stands really look like. It's kind of not rocket science when you think about it. You know, dead trees don't die and they continue to grow and use nutrients. So in Fool Creek, for example, this basin, half of this area is consisting of smaller trees that are regenerating, follow the cuts. And what that means in terms of basal area, if we look at our old growth stands and our mixed stands, they're all losing most of the large pine, but the percentage of large pine is higher in our old growth basin. So as a total, we're losing 40% or so of the basal area, which relates to leaf area and nutrient demand. And our mixed age stands, we're losing more like 20–25% of the total basal area. So we're just losing less, and there's more left around it. Kind of another way to look at this. We look at what the bugs are taking out. Over 90% of the trees that are smaller than 8 inches are sticking around. Over 90% of the trees that are greater than 30 centimeters are killed in these stands. So, and then finally, sort of the last piece of this glass half full picture. This is what our uncut stands look like following the beetle outbreak. These are live trees in the overstory, understory, and new seedlings. And this graph is kind of important for various reasons. One, for this nutrient retention piece, but also the question of will these stands remain stocked? And if you look at the new seedlings, new trees coming in underneath dead overstory, we see a large density, high density of young lodgepole. We see a lot of fir coming in, but in terms of U.S. Forest Service stocking recommendations of 370 trees per hectare, these stands are all, in these cases, these are almost all stocked. So we wouldn't be looking at kind of replanting problems in these areas. We can combine that with what's going on in the overstory and the sort of sapling size and add those trees back into the picture for thinking about the recovery of these stands as well. The other piece to look at is how the species composition changes a little bit. So our overstory in these stands is dominated by lodgepole pine. As we move down into the understory and our new seedlings, we're getting a higher proportion of fir, and that's something we'll follow up here in a bit. We're trying to kind of couple what we're seeing out in the landscape with these kind of nutrient responses. We see that we've got a much higher density of young fir in these stands that have not succumbed to the bark beetle, obviously, and we see larger numbers of pine as well in these mixed stands, and these are the trees that will be taking up any nutrients. We know from our ecophysiological studies that young trees use more water and nutrients per unit leaf area than our old stands, and in some cases they might be using over 5 times more on an aerial basis as the stands are developing. I guess that's what this is saying here down on the bottom. So these young stands are using quite a bit more water and nutrients. So kind of to package this stuff together, the question as we're trying to figure out where the nutrients went and whether or not we can explain our concern, we've got to sort of figure out, does this change in demand or growth in these young stands kind of accommodate the lack of a stream export question? If you look at and you kind of go back to the amount of increase, which is on the order of less than a kilogram of nitrogen per hectare per year of new nitrogen available in these stands. These forests are using more like 5 to 10 kilograms of nitrogen per hectare in their demand. So the sort of excess that was created following the bark beetle is sort of a small number and probably in the noise of the demand. So an increase in demand seems likely to be explaining this. And this kind of summarizes this first part, which is that we see differences we see nitrogen differences that vary with stand structure and species composition. So older stands are responding more than younger stands as a function of the size of trees, what's hit, the percentage of the basal area that's lost. We see significant increases in nitrogen, but they're small biologically, so interesting mathematically, but not biologically perhaps. And that it seems that the response of the trees in these basins can affect the retention of nutrients in these areas. And this is where this links in obviously with the management side. So if there's harvest going on, retaining good regeneration is obviously key. So at a new harvest kind of perspective, and then also thinking about how younger stands and older stands might act within broader landscapes to keep nutrient retention high. So the fact that we have these mixed age stands in our areas is a good way to kind of reduce the effects of the bark beetle more broadly.